Next up we have limiting reactants. I know it says equations and mole calculations here. I want to go back to our turkey sandwich example, and then we'll use this to help us understand what limiting reactant is. So go to the limiting reactant section in your notes. So going back to our recipe for a turkey sandwich, you need 2 slices of bread for every 3 slices of turkey to make 1 sandwich. So we have some ratios here. And so what about this? What if you had 10 slices of bread and 12 slices of turkey? So going back to we did these 2 separate examples. If you have 10 slices of bread and lots of turkey, you can make 5 sandwiches. If you have 12 slices of turkey and lots of bread, you can make 4 sandwiches. So what if you have 10 slices of bread and 12 slices of turkey? How many sandwiches can you make? 4, 5, 9, what is it? The answer is you can make 4 sandwiches. Well, why not 5? Well, you only have enough turkey to make 4 sandwiches. And so once the turkey runs out, you can't make any more sandwiches. So it doesn't matter how much bread you have. In fact, you're going to end up with leftover bread. And so this is the idea with limiting reactants. You take 2 arbitrary amounts of reactants, put them together in a reaction, and the amount of product that forms is limited by the reactant that disappears first. So I'll go to that slide in just a second. So 10 slices of bread, 12 slices of turkey, you can make 4 sandwiches. So this reactant, the one that is consumed completely, the one that runs out, is called the limiting reactant. It controls everything. So once that substance runs out, the reaction stops. No more products form, no more of the other reactant is used up. And so it controls everything. So that's an important thing we need to identify always, the limiting reactant. So let's go back to our last example here. So let's combine B and C. And I left you with this last time. What if you took 10 grams of iron 3 chloride and mixed it with 35.5 grams of silver nitrate? How many grams of precipitate will form? Well, again, if you have 10 slices of bread and 12 slices of turkey, how many sandwiches? That was 4. In this case, if you have 10 grams of iron 3 chloride and 35.5 grams of silver nitrate, how much silver nitrate will form? Well, the answer is 26.5 grams of silver chloride will form. So in this case, which reactant determined how much product forms in the reaction? And the answer is the iron 3 chloride. So the iron 3 chloride is our limiting reactant. The other reactants, the one that's not limiting, the one that you have leftovers of, the one that you have plenty of, is known as the excess reactant because you have leftovers or excess amount of that substance. So one of the reactants is a limiting reactant, the other is the excess. So in this case, the limiting reactant was iron 3 chloride, so our excess reactant is the silver nitrate. So again, we already answered letter C. How much of the precipitate would form? 26.5 grams or 29.9 grams? The answer is 26.5 grams. All right, so next question. A little bit tougher. How many grams of let's change the wording there. How many grams of, not the reactant present in excess, let's actually give it a name for this particular reaction. How many grams of silver nitrate? Isn't that our excess reactant? Will remain after the reaction is complete. Let's go back to our turkey sandwich example and we'll kind of work through with that example first. So here our limiting ingredients or limiting reactants is the turkey. And so what we need to find out, here, let's label this too. So this is our excess ingredient or excess reactant. First thing we need to determine is how much bread is needed to combine with the 12 slices of turkey. So if you have 12 slices of turkey, how many slices of bread will you need to make your sandwiches? So we have a ratio of 2 slices of bread to 3, whoops, that does not make sense. Let's fix that. 2 slices of bread to 3 slices of turkey. If you have 12 slices of turkey, you will need, and that's why I put needed earlier. So you need 8 slices of bread. Well, the question is, how much bread is going to be left over? Now, I know some of you are just giving me a number, but you need to show me where that number came from. So first, determine how much of the excess reactant is needed to react with the limiting reactants. And then we are going to subtract what you need from what you have. So we have 10 slices of bread, which is more than enough. You need 8 slices of bread, and so you're going to end up with 2 slices of bread left over or in excess. So let's apply this thinking to the other example. So first step, go ahead and solve this problem, answer this question. How many grams of silver nitrate is needed to react with the 10.0 grams of iron 3 chloride? Or let me word it differently for you as well. If you have 10.0 grams of iron 3 chloride, how many grams of silver nitrate is needed to react with it? Go ahead and set that up. Pause the video now while you do that. So if you have 10 grams of iron 3 chloride, you will need 31.2 grams of silver nitrate to react with it. Notice I put all these different words there. You don't have to put all of them, put any of them. That's what they mean. So 31.2 grams of silver nitrate will be used up, or 31.2 grams of silver nitrate is how much will react. This is not what we're trying to find. We want to find out not how much reacts, but how much does not react. Well, how much silver nitrate did we start off with? I believe that was 35.5 grams. So you have available 35.5 grams. You need 31.2 grams of that. And so subtract those, and that will give us how much is left over. So in this case, we have 4.3 grams of silver nitrates in excess, or left over after the reaction that is unreacted. All right, so let me kind of walk you through the entire process with a new problem. So I'm going to show you a little different technique as opposed to the last one. So consider the reaction for the combustion of butene, which has a chemical formula C4H8. We'll start off with the balanced equation, and then we'll do the problem. So go ahead and pause the video and write the balanced equation for the combustion of butene. Do that now. So there's our balanced equation. Here's the question. Suppose 13.0 grams of butene and 30.0 grams of oxygen were mixed and allowed to react. What would be the limiting reactant? Be careful here. Sometimes students will just look at which reactant is present in a smaller quantity. We don't do that because, again, we want to look at moles. And even the substance in the smallest quantity in moles isn't necessarily our limiting reactant, because we also have to look at the ratio in which they react. So let's go ahead and do this. Let's take each of those grams and convert to moles. So take 13 grams of butene and convert that to moles. Give me that number. And then we're going to take 30 grams of oxygen. Be careful, it's O2. And we're going to convert that to moles. So go ahead and pause the video, find moles of each reactant. All right, here's what we have. Number of moles that are available for each of our reactants. Next step is we want to find the what's called available mole ratio based on the amounts of chemicals that are available. So the easiest way, the best way to do that is take the bigger number of moles and divide it by the smaller number of moles. So let's do that. So we have 0.938 moles of oxygen per 0.232 moles of butene. Go ahead and pause the video and get to that number. Couple sig figs. 3 is fine. All right, so here's what we end up. We have 4 moles of oxygen for every 1 mole of butene available. Next step, compare what you have to what you need. You have 4 moles of oxygen for every 1 mole of butene. How much do you need? What you need comes from the coefficients in the balance equation. You need 6 moles of oxygen for every 1 mole of butene. So you need more oxygen than you have. Because you need more oxygen than what you have, that means that oxygen is our limiting reactant. Now let's just pretend for a second that we got 8 here. You have 8 moles of oxygen for every 1 mole of butene. And you need 6 moles of oxygen for every 1 mole of butene. If this were the case, then that means you have more oxygen than you need. If you have more oxygen than you need, then that means oxygen is the excess reactant and the butene is the limiting reactant. Now that's of course not the case. We need more oxygen than we have, so oxygen is a limiting reactant. That means oxygen controls everything, including how much water vapor should be produced. So once you identify the limiting reactant, use that as the given for the rest of your problems. So to do this calculation here, we only need to do one calculation since we know oxygen is a limiting reactant. We can start off with moles if you want. You can start off with grams or moles. So we have 30 grams of oxygen available. All of it reacts. Remember, the limiting reactant, all of it gets used up. We did, though, already calculate moles of that. So if we want to cut out a step, we can continue or start rather on our next calculation with moles of oxygen. Let's see if my pen will work. 0.938 moles of oxygen. We want to convert that to moles of water. So according to our balance equation, we have 4 moles of water for every 6 moles of oxygen. And then we want to find grams of water vapor that's produced. And that should get us our answer. Go ahead and pause the video, punch that up. All right, so you should, I use that word for a reason, you should make 11.2 grams of water in this reaction. All right, letter D. How much, again, let's change the wording there since we know what the excess reactant is. How much butene is present in excess? Let's restate that. How much butene should remain after the reaction is complete? So first thing we need to do is calculate the amount of butene that is used up or needed during the reaction. And then once we have that, we can find out how much is left over. I'll let you do that. Go ahead and pause the video. Actually, no. Let's do that together. So again, I'm going to start with the 0.938 moles of oxygen. So always start with your limiting reactants. This time our unknown, what we're trying to find is butene. So we have 1 mole of butene for every 6 moles of oxygen. And then we want to find grams of butene. So molar mass of butene was 56.1. All right, now go ahead and pause the video and see what you get for that number. So according to our calculations, if you have 30 grams of oxygen, you will need 8.75 grams of butene to react with it. Again, don't stop here. This is not the answer. The question asks for how much remains after the reaction. And so we started off with 13 grams of butene. And of that 13 grams, again, notice that not all of the excess reactant reacts. Only some of it reacts. The sum is 8.75, and we want to find out how much does not react. And so we end up with 4.2 grams butene in excess or left over after the reaction. All right, to give this one a shot all the way on your own, we have 15.0 grams of solid potassium. It's placed in a solution containing 30.0 grams of copper 2 chloride. This is a single replacement reaction. This reaction does occur. So write the balance equation for the reaction. Identify the limiting reactants as shown in the previous example. Find out how many grams of solid copper should form. How many grams of potassium chloride should form. And then how many grams of the excess reactants remain after the reaction. So go ahead and pause the video and work on all of that now. Let's go ahead and compare answers. Here's our balance equation. Found moles of each reactant. Took the bigger number of moles divided by the smaller number of moles to get our mole ratio. We have available 1.7 moles of potassium for every 1 mole of copper 2 chloride. We need 2 moles of potassium for every 1 mole of copper 2 chloride. Therefore, potassium is the limiting reactant. And so I just decided this time, instead of starting with moles, I just went all the way back to grams. It's kind of a waste of time. It's unnecessary steps, but I just wanted to show you. So if you have 15 grams of your limiting reactant potassium, how many grams of copper should form? You get 12.2 grams. How many grams of the other product should form? That's 28.6 grams. By the way, if you added those up, that would give you the total mass of the products. That is equal to the masses of the reactants. And so we know that all of the potassium is reacting. That's 15 grams. And then to find out how much copper 2 chloride reacts, we could take the 12.2 and add it to the 28.6. And then subtract 15 from that and get how much copper 2 chloride actually reacts. And so if you want, try that out. Instead, I went ahead and calculated it based on the amount of potassium that reacts. And so it looks like, because of rounding, you might get a little different answers, but 25.7 grams of copper 2 chloride is needed. You started off with 30 grams of the copper 2 chloride. So subtract what you need from what you have, and you will get the excess, 4.3 grams of copper 2 chloride that is left over unreacted after the reaction. All right, next up we have percent yield. Please don't confuse percent yield with percent error. Here are the terms that we're going to be using. First of all, the maximum amount of product that could be formed from a reaction is known as the theoretical yield. How much product should be produced? And I've used that term before, should be produced. So making notes, the theoretical yield for a reaction comes from a calculation. That's what we've been calculating. Every time we calculate the amount of product that forms in a reaction, that's a theoretical yield. So theoretically, if everything goes perfect in the reaction, there's no impurities with the reactants, that's how much you should make. So that's called a theoretical yield. How much product actually is produced in a reaction? Let's say you actually mix the quantities of chemicals and you weigh out how much product forms. In reality, that is known as your experimental yield. So the experimental yield can never be more than the theoretical yield. That doesn't make sense. How can you make more product than is theoretically possible? So it can never be more. It can be equal to the theoretical yield, but it's usually less because this is an imperfect world and we have impurities. Things don't go exactly as planned, and so usually your percent yield then is going to be how much? Well, ideally, what do you want your percent yield to be? If your experimental yield and theoretical yield are the same, your percent yield is going to be 100%. So with percent yield, you want a high number. As opposed to percent error, you want a low number. You want 0%. Here we want a high number. So let's take a look at the formula, see if I can squeeze that into my slide here. We take the experimental yield and divide that. Notice there's no subtraction this time. Don't subtract. This is not percent error. The experimental yield which, by the way, let's make a note about that. So the theoretical yield comes from the calculation. Where does the experimental yield come from? The experimental yield comes from one of two places. If you're actually doing the experiment, the reaction, you will, in the lab, weigh out the amount of product that forms. So it could come from the lab. What if you're not doing the lab? What if you're working on a worksheet or a test question? The experimental yield has to be given to you. You need to be told how much was actually produced in the reaction. So take those values and divide them. This is going to give you a decimal, and we want to convert that decimal to a percent. So we'll multiply by 100, and that will give us our percent yield. So instead of doing the next problem, let's go back and let's take a look at the last example. And let's say that the actual amount of copper produced by the reaction was 10.0 grams. So you perform the reaction, you separate the copper from the solution of potassium chloride, dry that solid, weigh it, and you get 10.0 grams. What is the percent yield then for this reaction? So our 10.0 grams is our experimental yield. Theoretically, so this is what we calculated before, you should make 12.2 grams of the precipitate. And we'll take those and divide them. 10.0 divided by 12.2 times 100, and you get about 82.0%. Meaning this reaction produced 82% of what it could have or should have produced if everything was perfect. All right, I think we'll stop there. I'll save that other example for you to work on in class, and then we'll have one more lesson on energy and mole calculations, and we'll do lots of practice. All right, thanks for watching.